Hello everyone, today let's solve the problem number 450, delete node in a binary search tree. So what the question states here, we are given the root of the binary search tree. See here, we have been given the root of the binary search tree here and an integer key. So here we have been given integer key as well, right? So we have to delete the node with the value from the binary search tree while maintaining the BST properly, right? So we have to delete the node with that node from the BST while maintaining the BST property, right? So here key we have been given 3 and we have to remove the 3. We have to remove the 3 from the binary search tree. The only thing is we have to remove the value from the binary search tree while maintaining the BST property. Still we have to maintain the BST property after removing it, right? So that is what we need to keep in the mind. If the node is not found, then we have to return the original tree. So if the node itself is not found, then we have to return the original tree. So we have to return the new root after deletion. So we have to return the new root after the deletion. Each node has unique values and the binary search tree is valid. Each node has unique values and binary search tree is said to be valid. So this is the question. See here, we have been given 3. So after removing 3, this part of 4, so see here, just give me a second here, 1 second. Yeah. So this part of 4 comes here to this place. 4 comes to this place basically. Now this has been 5, 4 to 4. Still we can move here because binary search, this one binary search tree property, the left node to the root node, the value of the left node has to be smaller and the value of the right node to the root node to be greater. So to be greater or larger, to be greater or larger, not times, sorry, larger basically, right? So here we can just move 4 here. So this would be 5, 4, 2 and this remains same, 5, 6, 7, right? So this has to be larger, right? So same thing, 5, 6, 7. This is fine. So let's move on with the second example here. So same thing they have given in the explanation as well. So given key to delete 3, we have, so we find the node with 3 and delete it. One valid answer is 5, 4, 6, 2, double null 7, double null 7. This one shown in the above binary search tree. Please notice that another valid answer is this one. We can consider this one as well. So they have given diagram again, I guess. So let just give me a second here. See, this is also valid answer, man. We can keep the 4 as it is here, right to the 2. So we can just move this one too. So this is also valid. See here, just give me a second. So we can just move 2 to here and 4 we can just move, this one becomes 2 and this one 4, right? So this, however, we need to remove 3. So 2 is lesser than this one, 2 is lesser than 5 and 4 is at the right side of the 4. This becomes null basically. This becomes null. We don't have to represent this one, right? So here 5 to 4. So 2 is less than 5, binary search tree. This is binary search tree. The left node has to be smaller, right? So the value of the left node has to be smaller. So this is fine. So this is 2 here in this case, right? So 2 and this can be 4 because the right node of the right node to the root node, the value of the right node to the root node has to be larger here in this case 4, right? So this will be null. So this we don't have to represent this one at all. So this is also actually what do we call, valid. So this one we can represent in this way, 5 to 4. So this remains same, man. This one 6 and 7, 6 and 7 remains same here. So this part I'm speaking of, 6 and 7 remains same. So this is nothing but 4, 5 to 4. So this is fine. So let me remove this one entirely. Let me remove this one entirely. So now let's move to the second example. You can just check it out in the same way for the second and third example. And third example I want to consider here because we have been given 0. So I mean key that we need to remove is 0 and we don't have any elements within the root and we just have to this one return the empty array in this case, right? So in this case, so they have given us wonderful examples just for the sake of understanding. Now as we are completely this one familiar with the question, let's discuss the approach. Let's discuss the approach followed by the complexities and then let's write the code. For this one, for the approach, I'll just consider the same example, the first example that they have given in the question. So just give me a second here. So yeah, we have this one, right? 5, 3, 6, 2, 4, null 7. This one we are considering, right? So the input. So first step here is we will start from the root 5. This one I'm speaking of, we will start from the root 5. We'll start from the root 5. So key we have been given 3. So key we have been given 3. We'll start from the root 5. So this one key, basically key 3 is less than 5. 3 is less than 5 means key is less than 5 or 3 is less than 5. So that is the reason we will go left. We will go left, right? So 5 means here key we have been given 3. 3 is less than 5. That is the reason accordingly with the binary search tree. So the root of the left node, this one has to be smaller, right? So the value of the this one left node to the root node has to be smaller. So we will check for the left node. We'll check with the left node. So we have found the value 3 here. We have found the value 3 here. So node 3 has two children. Node 3 has two children here. One is 2 and another one is 4. One is 2 and another one is 4. Right. So you can clearly see here. Right. So we will find in order successor. So we know the in order, pre-order and post order, right? So we have solved the problems on it already. So we will find the in order successor, which is 4, smallest in the this one, smallest in the this one I'm speaking of, smallest in the what do we call right subtree. So we will replace 3 by 4. We will replace 3 by 4. Instead, this one 3. So we have to remove 3, right? So we will go with the in order successor, which is 4, basically. So we will replace 3 by 4. We will replace 3 by 4. So same thing, we will recursively delete 4 in the right subtree of 3. We will delete the this one. What do we call? We will delete the 4 in the right subtree of 3. We will recursively delete the this one. We will recursively delete the 4 in the right subtree of 3. Right. So now this will be 5, 4, 2 and this remains a same. 5, 6, 7. 5, 6, 7. Right. Final subtree we can write 5, 4, this one. 5, 4, 6, 2 here null, this is null, 2 null, null 7, 2 null, and again here we have this one. For this also we have null here. So basically this will be null, 2 null. So I'll just write null here, 2 null, null 7, 5, 4, 6, 2 null, null 7, the final output. The same output, the output that we got here is 5, 4, 6, 2 double null 7, which is equivalent to the output that they have given for the this one, example 1 within the question. So our approach works absolutely correct in this case. Our approach works absolutely correct in this case. We went with the in order successor, basically. In this case we went with the in order successor. So we have another method as well, I mean another way of doing the thing as well. So they have shown in the diagram, you can just do it in that way as well. So I insist you to try out with the different methods or the different approach if you have, right? So you'll understand the question better. Maybe your intuition might work in that case. Maybe your intuition may be better than mine, right? So you can just go with your own intuition. So that's what. So here we are done with the approach part. Now we are done with the approach part. Let's quickly discuss the complexities and then let's write the code, right? So what will be the time complexity here? The time complexity would be big of h. So we can consider big of n. Still I'll just go with the h because this is the safer side. So h is nothing but the height of the binary search tree, right? For the worst case, if we consider for the skewed tree, it will be big of n. And for the balanced binary search tree, it would be big of logarithmic n. Binary search tree. The name itself indicates that binary search tree. So quite obviously, it is of the this one. Time complexity would be big of logarithmic n for the balanced binary search tree, and for the worst in the worst case for the skewed tree it would be big of n. So it's better to consider big of h rather than the big of n for the worst this thing, right? For the worst binary search tree, or the for the in the worst case for the skewed tree, rather than to consider for the skewed tree, it is better to consider the big of h. So here the time complexity would be big of h and the space complexity would be big of h as well, because the recursion stack can take up to big of n, and instead of going with big of n, it is better to go with, again it is better to go with the big of h, nothing but the height of the binary search tree, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of h, big of h for both. So now we are completely familiar with the approach and complexities. Now we are good to write the code. Let's start writing the code. So the first step here would be, so let's go with the base case, means for the empty tree. If the tree doesn't consist of any root, or if root is null, then we have to return null. This itself is the base case. Let's write this one. If root equals null, then we have to return null. This is fine. So the next step is if key less than root dot value, then what we will do, then the key is in the left subtree, means I'll just go with root dot left here. This one will be, let me consider delete node here. Let me give delete node here. This will be root dot left comma key. This is fine. So the next step would be, let's go with else if here, if key greater than root dot value, then what shall we do? Here key is in the right part of the key is in the right part, or key is in the right subtree. So then I can just copy the same thing and let me make the necessary changes over here. So this one will be, instead of left, I'll just change this one to right. So we are going with the recursion right here. This is nothing but root dot right comma key. So else 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 this is binary search tree, so we can write in this way directly, right? So this is fine. Else if we have found the node that is to be deleted, then we have two cases. One is, we have to go with the node with only one child or no child. The second case is we have to go with the node with two children. These two things. So both the cases they have shown for the example one. Either you can go in this way, or you can just go in this way as well, right? The first case is we have to go with the node with only one child or no child, or we can just go with the node with two children. Means we have to get the in order successor, smallest in the right subtree. Basically we went with the case 2. I showed for the case 2 in the approach mainly, right? So let's go with the case 1 here. Nothing but we have to go with the node with only one child or no child, right? So here this will be if root dot left equals null, then we have to return root dot right. So this is fine. Else if mm, root dot right, so this is equal to null, then we have to return root dot left. This is fine. So the next step would be, so just give me a second, man, here. uh yeah, then the next step would be here, we have to go with the node with two children. Means we have to get the in order successor. Nothing but we have to go with the smallest in the right subtree. We have to get the in order successor. Nothing but we have to go with the smallest value in the right subtree. Here I can just articulate in the form of code in this way. Tree node. So this one will be min node equals find min, this one root dot min, find min of root dot min. So this is fine. So the next step would be we have to replace the roots value with successors value. So here this would be root dot value equals min node dot val. So this is fine. So the final step would be we have to delete the successor in the right subtree. Means I'll just go with the root dot right. Here this one will be delete node, as we are going recursively. This one will be root dot right and min node dot val. Root dot right comma min node dot val. This is fine. So we are done with all the logical part, mostly. So here Feynman, we have made use of the Feynman directly, man. Here I forgot completely. So here Feynman, we have made use of the helper method Feynman, but we have not written the code for the Feynman at all. So let's write that one. Sorry, I just completely forgot that one. I'll just go with private tree node. So this will be Feynman of tree node. So this is fine. Within this method, we have to go to the leftmost node. Means I'll just go with the while condition here. Node dot left not equal to null. So node equals this one, node dot left, node equals node dot left. Let me return node, let me return the node. So this is fine. We have already made use of the find min here. Min node, we have assigned this one to the find min of root dot min. So this is fine. Finally we were left here, right? So where we ended up here, this one, we are deleting the successor in the right subtree, this one, right? Root dot right. So yeah, now I'm able to remember this one. The next part is finally we have to return the root. So finally we have to return the root, right? The final answer after deleting the key, this one, key from the tree. So finally we have to return the root. So let me format the code once and let me hit the run button. So we have the compile error here. Tree node min node equals find min of root dot min. What we have here? Variable min, line number 17. Just give me a second here. So what we are doing here? Return root dot left. So where is this? Just give me a second. Completely get lost sometimes, man. So just give me a second. If root dot left equals null, then root dot uh, right, then right. This is fine. Oh, we are in the second case, right? So here, so what I am doing here? Find min of, oh, root dot min. Why I have given this one has to be root dot right. So here we are getting the in order successor man, means we have to get the smallest in the right subtree. So this has to be root dot right. Find min of root dot right. We are going with the right side. So yeah, now it has to work. Let's see. So again we have the error. Cannot find the symbol. Method find min. So did I give capital M here? Yeah. Let me give capital M. Also now this has to work again. Thank God I found out this one as well, or else we would have got the wrong this one output. So yeah, here this is fine. The sample test cases are getting passed. So let me hit the submit button, man, quickly. So here you can clearly see all the test cases are getting passed, means the code works absolutely correct in this case. So the code works absolutely correct in this case, right? I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.